On Tuesday, we talked about finding the area under a curve. And what did I mean when I said area under a curve? Yeah, it was the rectangles between the curve and the x-axis. Okay, so let's go ahead and write that at the top of our paper just so we don't forget. The area under a curve really means between the curve and the x-axis. All right, when we looked for delta x, anyone remember that? You might have to look at your homework packet. B minus A over N. And what were the B and the A and the N? So the B and the A came from the interval. A was the lower bound of the interval. B was the upper bound of the interval. And then N was the sub-intervals. So the number of rectangles that you were using to find the area underneath your curve. The more rectangles you have, the more accurate the area. When you have infinitely many rectangles, that's when your area is perfect. Okay. So delta x is b minus a over n. What was xi? This one was the one that was maybe a little bit more confusing. Yeah, it was the delta x times I plus,
the y value, right?
not the y value, not the b, the a, the lower bound. And this is kind of like y equals mx plus b. So it's the change, how wide your interval is how your x coordinate is going to change, multiplied by the x value that you're on, plus the starting value. So it's kind of like y equals mx plus b. Okay, so those are the little formula pieces that we referred to before. We're going to keep doing them again today. Remember what I said on Tuesday was that this is something that you might not understand all at once. It's more like the more we use it and I continue to explain it, you'll start to be like, that part kind of makes sense now. So hopefully today we'll have a lot more understanding starting to happen. Okay. So we looked at the limit of sums on Tuesday, which was written as the limit as n approaches infinity. So that means that as we get more and more rectangles, we're trying to have as many rectangles as possible because we know that's what makes our area the most accurate. Then we're going to say we're multiplying delta x, which was the width of each rectangle, times the height of each rectangle. And if you guys remember, when we did width times height, width times height, width times height, the width ended up being a GCF, and so we pulled it out to the front. Mm-hmm. So this is kind of like having the width pulled out to the front. And then we have a summation because we were multiplying it by multiple heights added together. Okay, so this is the width pulled out as a GCF. Then this is the summation of all of the heights added together. So we say I equals 1 to n. So if our sub-interval said we have 4 rectangles, then we would do the first rectangle plus the second plus the third plus the fourth. If we had 5 rectangles, we would say from 1 to 5, right? The first plus the second plus the third plus the fourth plus the fifth. If we're doing infinitely many rectangles, that's why we have 1 to infinity. So we're saying all the rectangles added up together, okay? And then here we say f of x sub I. And the reason that we say f of x is here is because the height of each rectangle was found using the y coordinate of the curve at that point. So we said the width of the rectangle multiplied by the height, and the height was the curve.
So the xi is the y?
The xi is saying we had this stuff right here, whatever you figured out that you had to plug in to get your y coordinate. Mm-hmm. So when we were saying our intervals were a width of 1/2, then you might plug in 0 first, and then 1/2, and then 1, and then 1.5, and then 2. And so this is just saying plugging in whatever you're supposed to plug in. Okay. So that was the formula that we looked at. Now, this is actually the limit definition of an integral. So we looked at, when we learned about derivatives, we did the limit definition of a derivative. This is the limit definition of an integral. So the nicer way to write this, and the way that's going to become more common that you'll probably like better, is we say the integral from a to b, and this right here is the integral symbol, and it looks like an S because it means S for sum. So instead of writing the sigma notation and the limit and all of that, we just say S for sum. Here's our lower bound, here's our upper bound of f of x dx. And so instead of writing all of this stuff out, we're actually going to write this, which looks a lot nicer and cleaner. It's definitely easier to write. Okay. How are we tracking so far? Maybe some things that weren't are starting to clear up, hopefully, and I'll keep explaining. Okay, so we're going to go ahead and describe what all this notation stuff means. I guess I didn't really need to write notation here because we can just draw arrows. So I'm just reminding you that this right here is the width of the rectangle. This right here is the height of the rectangle. And then this is saying that we're doing infinitely many rectangles or subintervals, because each subinterval made a rectangle. Okay, for this one, this part right here, this is representing the curve, so this represents the height of the rectangle. The dx on the end represents the width of the rectangle, and it never changes. It is always written as dx. Okay? And then the a and the b, you can see, are your upper bound and your lower bound. Okay? So the lower bound goes on bottom because it's lower, and the upper bound goes on top because it's higher. And since this is the way that we're going to like super shorthand what we have been learning since Tuesday, since this is like a super shorthand of that, this is the exact area under the curve. And that means that when we write this integral notation, the assumption is we are using infinitely many rectangles and we are finding the perfect answer every time. So we are no longer approximating, we have the exact perfect right answer. Okay? All right, so now that we're going to go and look down here, we've switched from that limit notation to now we're using this integral notation. So when they say this, the integral from 0 to 4 of f of x dx, what they're saying is find the area underneath the curve from 0 to 4. Does that make sense? Area under the curve from 0 to 4. Now, if you have a curve to plug something into, then you're going to use this idea of width of a rectangle and height of a rectangle, and if we don't know how to do these by hand, which we won't know how to do for another few days, then we'll do our best to approximate it. It's kind of like back when we were finding the derivative of something, we would sometimes use the old school slope because we didn't have enough information. Sometimes we're going to have to revert back to those rectangles and we'll approximate it as best we can. But eventually we'll know how to do all these by hand and we'll get perfect exact answers every time. Okay? So right here it just says the area underneath the curve from 0 to 4. And if you look at the picture from 0 to 4, that's actually half of a circle. So we don't need to use rectangles to approximate that. We can find the area of the circle to approximate that. Okay? So since it's half of a circle, I'm going to say 1/2 in front. And then what's the formula for area of a circle? Pi r squared. So I'm going to say 1/2 times pi, and then I need my r, and then I'm squaring it. And I'm going to go ahead and get a marker out so you guys can see exactly what area we're trying to find here. So if we're doing the area underneath the curve from 0 to 4, then that is the area that we're finding right there. So what is the radius of that circle? 2. So we're going to say 1/2 times pi times 2 squared. And so what would that area be? 2 pi. Yeah, 4 times half of a pi would be 2 pi. So the area from 0 to 4 is 2 pi. Okay. Next, they want us to find the area looking from 4 to 8. So if we look from 4 to 8, I can't find all, well actually I could find all of it at once if I know the formula for a trapezoid. Anyone know the formula for a trapezoid? Nope, that's okay. So instead of doing that, let's go ahead and break this up into some triangles and rectangles. So if we look at this first part right here, that's a triangle. How do I find the area of a triangle? Yeah, 1/2 base times height. So I've got 1/2. The base of this triangle is 2. The height of that triangle is 2. So 1/2 of base times height. Okay, so that one's done. Then next to it, I have a rectangle. How do I find the area of that rectangle? Yeah, just base times height, so just 1 times 2. Okay, so that one's done. And then next to that rectangle, I have another triangle. And that one is going to be 1/2 base times height. So plus 1/2. The base is 1, the height is 2. Okay, so if we were to add up all of those to get the overall area, 4 times 1/2 is 2. 2 plus 2 plus 1 gives you an area of 5. So someone said that. That was good. Okay. Did somebody say 3? Oops. It's okay. We just came back. We're a little bit rusty and everything. Okay. And then last, we have the area underneath the curve is this triangle space right here. Now this is underneath the x-axis. So what does that mean about our area? It's negative. Okay. So I'm going to say this right here is a negative answer. We have the base, which is 4, so minus 1/2 times the base of 4 times the height of 2. Okay, so negative 1/2 times 4 times 2 is negative 4. Okay, so we have all 3 of those areas, right? We did them separately. Now they're saying they want the area from 0 to 8. So if they want the area from 0 to 8, then they want this green part and this red part. So just add them up. We have 2 pi plus 5, and that's it, because those are not like terms, so you can't add them any better than that. Okay. What if they want the area of the whole thing? The green part, the red part, the pink part. So we're going to say 2 pi plus 5 plus negative 4. What does that give you?
2 pi plus 1.
2 pi plus 1. Okay. So anytime you're given a problem like that where they give you some shapes and you don't have a curve, finding the area under the curve literally just means finding the area of all those shapes, like adding them up. Okay. So example 2 wants us to represent the area under the curve on that given interval, and they want us to use the definite integral, which is the new notation we're using today. They also want us to use a limit of sum. So we're going to write it both of the ways that we know how. Okay? So I'm going to go ahead and shade this area from 0 to pi, because that's what we're representing. Right in here. All right, do you guys have a certain notation you'd like to do first? The new one. Okay. So when we do the definite integral notation, we say the lower bound to the upper bound. So what was the lower bound for the interval? 0. So we're going to say from 0 to pi. Okay. And then we say the function. So the function was x to the third plus x times sine x. And I'm going to put that in parentheses, x to the third plus x times sine x. And that represents the height of the rectangles. And then what do we write to represent the width of the rectangles? Dx. So we say if you have infinitely many rectangles representing this area, infinitely many rectangles representing the area from 0 to pi, then to find the area you do height times width for all those rectangles. And the S means we're doing the sum of all that stuff, we're adding it all up. Okay, so that's like super duper shorthand. Now we're going to go ahead and do the limit notation for that. So first when we do the limit notation, we're going to find our delta x. So how do we find delta x? B minus a, so upper bound minus lower bound divided by n. So that means our delta x is pi over n. And then we also have to find our x sub I, which is, they're very close. They are often the same thing. Yeah, so it's pi over n times I, and then it's plus the lower bound, which is plus 0. And we've done a lot of problems that had a lower bound of 0, which is why these two are almost always exactly the same thing, except this one has the I in it. Okay, so we're going to say the limit as n goes to infinity of the width of the rectangle, which is our GCF pulled out in the front. So where does the width of the rectangle come from? It's the pi over n, it's the delta x, right? So pi over n is like that GCF we pulled out to the front. Then we have summation because we have all the different heights added together. So we have I equals 1 to n. And it's f of xi. We know that f of x is x to the third plus x sine x. So what we're going to do is we're going to say x to the third, well f of xi, if I was to take this and plug it into the function, I would get pi over ni plus 0. Do you guys want to write the plus 0 or leave it off?
No.
Leave it off? So x to the third plus x times sine of x. I'm going to put brackets around that so I know that that's like the whole thing that we're doing the summation of. So these are two different sets of notation that are telling us the exact same thing. It's kind of like when we've been doing those AP style problems for derivatives, where instead of saying f prime of x, they do the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. It's exactly the same thing where when you see that notation, you think in your head, aha, that's a derivative. Same thing here. When you see this in your head, you're going to say, aha, that's an integral. Yeah.
What does the I mean again?
The I is saying like the term that you're on. First term, second term, third term, or not the term, but the rectangle that you're on.
Okay.
Like first, if you're adding just one rectangle, or if you're using two rectangles to approximate your area, or 3 or 4 or 5.
So that's why we would do like r to the 4 or r sub 4 and all that stuff.
Yep. Yep.
So it's more a variable than the I that we use for.
It's not an imaginary number.
Yeah, it's not an imaginary.
Yeah, so it's used here as just saying, and they could use I, they could use K. They could, I and K are the number or the letters I typically see in that situation.
Yeah. But it just depends.
It just means whatever number you're on. Okay, go ahead and flip the page. All right, so the next two examples are going to show us going back and forth between the two notations. Okay, so this one gave us the integral, the definite integral, and they want us to write it as a limit of sums. Okay, so that means that we need to be able to find our delta x, and we need to be able to find our x sub I. Those are the two things that we always need so that we can write the limit of sums. So delta x is the upper bound minus the lower bound divided by n, right? So what's your upper bound?
3 ends.
Oh, 3 over n? You were just telling me the answer.
Yeah.
So it'd be 3 minus 0 divided by n. which you're exactly right was 3 over n. Okay, and then what is our x sub I? 3 over n times I plus 0, because that's our lower bound. Okay, so we have the limit as n goes to infinity of the width of the rectangle, which is 3 over n, there's the width, times the summation from I is 1 to n. And then we have to think about the function that we're plugging all the stuff into. Okay, so it's going to be 3 over ni cubed minus 6 times 3 over ni. I'm going to put brackets around that. So this is representing the width of the rectangle. This represents each of the different heights of the rectangle. Okay. And again, it's written like that because when we did width times height plus width times height plus width times height plus width times height, the width was a GCF we could pull out to the front, and then we just had a bunch of different heights we were adding together. All right, so that's the answer to that one. Okay, let's look at this one. So our delta x is, again, it's 3 over n again, but if we show our work, we're going to say upper bound minus lower bound divided by n, and that's how we get 3 over n again. This time the x sub I is a little bit different, right, because we actually have a number for our lower bound instead of 0 for our lower bound. So we have 3 over ni plus 2.
If it was a negative 2, would you write minus 2?
Yes. Okay. So we have the limit as n goes to infinity of our width, 3 over n, times the summation from I equals 1 to I equals n of, and this is where we take our function and we plug stuff into our function. 3 over ni plus 2, and this is to the 4th power because our function was x to the 4th. And this time you do not need brackets around it because it was just one term. It wasn't multiple terms. Okay. How do your brains feel about that so far? Relatively okay? Okay. Now for the other one, we're taking the limit of sums notation. We're writing it back into the integral notation, and this is a little bit more complex because things are not as obvious in this notation. So we're going to do exactly what we did last time. First, we're going to look for our delta x, and we're going to look for our xi. Because if we can find our delta x and our xi, then we can figure out what the b value is and what the a value is. And that's really important to pick out those a and those b values. They're a little bit hidden in the limit notation because they've been subtracted and simplified. So that's why we have to do a little bit of work to figure out what they are. And we can just go ahead and plug them back in. So our delta x is right here in the front. It's pi over n. So that means that b minus a over n somehow equaled pi over n. So that means that b minus a has to equal pi. So it could be pi minus 0, it could be 5 pi minus 4 pi, right? That would have given the same answer. It could have been 0 minus negative pi. Does that make sense? So we've got options. It's probably pi minus 0, but we know that we have a few different options. We just know that that's the first part, okay? The second part is we can look at the xi, and we have pi over ni plus 0. That's why they didn't write anything after it. And so this plus 0 right here tells us that our a value is 0. So that's why we have to look at the two things together, because we have to know if the a value truly was 0 or if the a value was negative pi, or if the a value might have been 4 pi or something like that. Then our b would be based off of that. Okay, so our lower bound was 0, so that means that b minus 0 equals pi, and so b has to equal pi. Okay. So it was your first guess, but we had to look at two pieces of information to make sure. Okay. So we can go ahead and write our integral. Our lower bound is 0, our upper bound is pi. And now we have to pick out what the original function must have been. So if you look at this, they plugged in pi over n times I here, so there must have been an x right there. And then they plugged in a pi over ni right here, so there must have been an x right there as well. And so our function is x to the third plus cos x. Yep. So this right here, I'm going to put parentheses around it. That represents the height of my rectangle. We always plug something into the curve to find the height of the rectangle. The dx, as you guys said, represents the width of the rectangle. Okay? And remember, this s right here means the sum. So we're finding all the rectangles from 0 to pi, using this as our height and this as our width. And we're doing the sum of all that stuff. So it doesn't really matter which notation you're going back and forth between. Your first step, either way, is to look at your delta x and your x sub I. We did that both times. So in one situation, it was so we could plug it in. In the other situation, it was to see what they used to plug in so that we could undo that work. Okay, so for b, we're going to do the same thing. We're going to say our delta x, again for this problem, is pi over n. There is a typo on this that I didn't catch until after I made copies. So take this, this parenthesis right here and scribble it out. This parenthesis should have been after the pi. Should have been right here. Okay, so again, if the delta x was pi over n, that means that b minus a must have equaled pi, right? Because it's b minus a over n, so that must have equaled pi. And then the x sub I is pi over ni plus pi. And since the x sub I is pi over n I plus pi, what is the lower bound? Yeah, so a equals pi. So b minus pi equals pi. So b must have been 2 pi. Okay, so for the integral, we have from pi to 2 pi. And what is, I'm going to go ahead and say this is where the x was plugged in, this is where the x was plugged in. What is our function? Yep. So same function as last time, they just had a different interval that they were finding the area on. So there's the height of our rectangle, dx is the width of our rectangle. Okay. We are going to stop taking notes there for a little bit just so you guys can practice the two different notations. Okay? How do we feel about the two different notations right now? Okay. Maybe not awesome still, but a lot better than Tuesday. You kind of understand where it all comes from? Okay. All right. Wherever you're at on 1 or 2, we're gonna stop there because I think that you guys can handle doing some of those on your own if you need to. What I want you to do is I want you guys to take a moment and I want you to break this up and find all these areas right here so that we can do number 3 together because I think we're going to need to talk about some of these problems. Okay. So go ahead and take a moment, find all your different areas underneath this so that we can use them to answer the questions. Okay. How'd you guys do as far as finding your little areas?
2 pi minus 6.
So what's this whole negative area down here?
It's -6.5.
Yeah, so -6.5, or you could say -6.5. And then this was half of a circle, so 2 pi right there. And then +1/2 right there. So if we add up all of those, -6.5 plus 2 pi plus +1/2.
2 pi minus 6.
Yeah, 2 pi minus 6. Or you could say -6 plus 2 pi. Doesn't matter. Okay. So if we do this, we're literally saying the area underneath the curve is the summation of all of the rectangles from 0 to 10, however many rectangles you choose to make, infinitely many, to get the correct area. And it's saying that this is the height of the rectangles and this is the width of the rectangles, right? So the height of the rectangles is represented by velocity, which is centimeters per second. The width of the rectangle is how much time, which is seconds. So if you're multiplying those to find your rectangles, you're doing centimeters per second multiplied by seconds. And the seconds cancel out, and so your answer's units are centimeters, okay? So it is 2 pi minus 6, and then all of those have the units of centimeters. So this number represents the distance that you are from the initial position. At 10 seconds, where are you in relationship to this starting position? So the starting position is 0, the ending position is 10. This is saying where you are at 10 seconds. Okay? So we're going to say the location of the particle at 10 seconds. Okay, and that is from the original position, which was at 0 seconds. Okay,
So our total distance is 10
not total distance. It's how far you are from that starting position. Remember, there was a difference in wording between total distance traveled and your displacement. Remember? So when I lived in Raleigh, I traveled 20 miles to and from work each day. So my total distance traveled was 40 miles. But when I'm sitting at work, my displacement is 20 miles. I'm 20 miles away from my home. This is displacement. How far away from your original position are you? Okay? The reason it's displacement is because the particle travels left first. This is going left because it's negative. Remember, a negative velocity means it's going left if it's traveling horizontally. If it's traveling vertically, it means it's going down. So it traveled to the left first, then it traveled to the right. So when we're adding up those values and we're keeping the left values negative and the right values positive, then we're saying we started off here, we went left for a little bit, we went right for a little bit, we came back here. That's not describing my total distance that I've traveled, that's describing how far I am from the beginning. So this right here, the location of the particle at 10 seconds, we're going to say that's displacement.
And the 2 pi minus 6 is?
The displacement.
Okay.
So that's when I'm saying I live 20 miles from work, and so when I'm at work, I'm 20 miles away. That's a displacement value. That's not how far I traveled that day. That's how far I am away from my home.
Okay.
Okay. Now, the total distance traveled, that's when we say, let's take the absolute value of all the different lengths that I've gone, because that would add up. I went this far to the left, I'm counting that. Then I went to this far to the right, so I backtracked. Then I went this far to the left. So for us to find the total distance traveled, we're going to use the absolute value of the 6.5 that went to the left, because we want to count that as an actual distance. We don't want to add it to something positive and undo some of that. So we're going to say negative 6.5 plus 2 pi plus 0.5. And so what is the total distance traveled for the whole thing? The whole entire thing. Say it again? Yeah, 7 plus 2 pi. And again, that's centimeters. So the first one is displacement, because I'm saying how far back and forth I've gone. It's the absolute value of negative 6.5, which is positive 6.5. The absolute value, because we're not saying how far back and forth am I going. We're saying just how far have you gone. So this is 6.5. and another 0.5 makes 7, and then 2 pi. So we're counting all positive values. That's how we count the total distance traveled. Now the part that says when is the particle speeding up, we have to think about when things are speeding up versus slowing down. Do you guys remember how to know it was speeding up?
Increasing, right?
Not just, it's 2 pieces of information. It has to be, it's speeding up if the velocity is positive and the acceleration is positive, or if the velocity is negative and the acceleration is negative. Okay? So this is a graph of velocity. That means that the velocity is positive when the graph is above the x-axis. It is negative when the graph is below the x-axis. Okay? When we look at the velocity graph, what do we know? How can we answer questions about acceleration from the velocity graph? It's the derivative of velocity. What's another word for derivative? Slope. So when the graph has a positive slope, the acceleration is positive. When the graph has a negative slope, the acceleration is negative. Okay? So underneath this, we're going to interpret this a little bit because this is, it's not mathematically impossible, but it's going to mess with your brain. Okay? So speeding up is where the velocity is positive, and we just said the velocity is positive when the graph is above the x-axis. Okay? So this is above x-axis, and so we said that you're speeding up if your velocity is positive and your acceleration is positive. So for us, that means that on the graph itself is above the x-axis and has a positive slope. Above the x-axis is where the velocity is positive. Positive slope is where the acceleration is positive. Okay? So you can be speeding up if you're above the x-axis and you have a positive slope. Or you can have a negative velocity and a negative acceleration, and that would be speeding up as well. So that means that we are below the x-axis and have a negative slope. So that's what we're looking for speeding up. Now, even if I wasn't a teacher, right, even if I wasn't explaining this for you guys, I would still write that down before I did the problem because it would mess with my brain too much to try to keep track of that and do the problem at the same time. It's just like it seems really abstract, so it's hard to picture, okay? Slowing down means that your velocity is one sign, positive or negative, and your acceleration is the other, okay? So for slowing down, that could mean that you are above the x-axis and you have a negative slope. So above the x-axis would mean that the velocity is positive, but a negative slope means the acceleration is negative. Or you could be below the x-axis and have a positive slope. So below the x-axis would mean your velocity was negative. A positive slope would mean your acceleration was positive. Okay? All right, so if we look at this first part right here has a positive slope, but it is underneath the x-axis. So is it speeding up or slowing down? Slowing down. So from 0 to 2, we are slowing down. Okay? From 2 to 4, the slope is constant, and that doesn't tell us speeding up or slowing down.
It's just like the same.
That's saying it's traveling to the left and it's not accelerating. You've hit cruise control.
Okay.
Okay, so you're not slowing down, you're not speeding up, you're traveling the same direction. Okay? Now here we have another little piece that's beneath the x-axis, but has a positive slope. Slowing down. It's slowing down. So from 4 to 5, particles slowing down. Okay? Now here we have a piece that is increasing, it's positive, got a positive slope, and it is above the x-axis.
So it's speeding up.
It is speeding up. From 5 to 7, we have a positive velocity and a positive acceleration, speeding up. Okay? From here to here, we are above the x-axis, but with a negative slope. Slowing down. And then that last little piece is above the x-axis with a positive slope. Speeding up. Okay. how much does the particle move to the left? 6.5. All right. If they wanted to know how much it moved to the right, what would we say?
Plus 2 pi.
Yeah, 1/2 plus 2 pi. Yeah. Okay, so how much does the particle move to the left? That's 6.5 centimeters. What is happening at 7 seconds? Say it again.
I said change direction first, but now I said change speed. Yeah, really.
So it wouldn't be changing directions because left to right happens at x-intercepts, right? Velocity is negative, then velocity is positive. That's left to right. The slope is 0. What does it mean if the slope is 0? It's constant speed. That means that it's not accelerating or decelerating. Okay? So we're going to say at t equals 7, I'm going to say v prime of t, so the slope of our curve is 0. That really means that the acceleration is 0. So we're going to say what's happening? No acceleration. For a split second, there's no acceleration there. Okay, go ahead and flip the page. So, for these questions right here, it says to write the definite integral for the following. I want you to add to the instructions and the limit of sums. Find the definite integral and the limit of sums. I want you to do both. Okay. So if we were to do the integral for this one, what is our lower bound for number 4? -2. What's our upper bound? 3. Okay. So lower bound is -2, upper bound is 3. What's our function? X to the 4th over 8 minus x to the 2nd over 2. And then what do we stick on the end? Dx. Okay? X to the 4th over 8 minus x to the 2nd over 2. Okay? That's our integral. I also want you guys to write the limit of sums. So what information do I have to find to do the limit of sums? Delta x. So that is b minus a. That's going to be 3 minus -2 over n. So 5 over n. And then what's our xi? 5 over ni. Yeah, plus -2, or you could just write -2. Okay. So our limit of sums would be the limit as n approaches infinity of 5 over n Okay. And then we're plugging stuff in for x. What are we plugging in for x? So 5 over ni minus 2 to the 4th power over 8 minus 5 over ni minus 2 to the 2nd power over 2. Putting that in brackets. So those are our two different forms. Yeah. And the nice thing is eventually we will move away from the second one and mostly use the first one. But we're going to come back to it every so often. The second form, that limit of sums, it used to not be on the AP exam. Now it is. So we have to make sure we're okay with it. Okay. It is not all over the AP exam, though. The first form is all over the AP exam. The second form is not. It'll just show up every so often. Okay, we're gonna look at number 6 because number 6 gets a little weird. What is interesting about number 6? The interval is based on the y-axis instead of the x-axis. You guys see that? So it still has a lower bound and an upper bound, it's just like on the y-axis. That means that when we write our definite integral, it has to be in terms of y's and not x's. Okay? So that means we need to rewrite our function so that it is an x equals equation, so we're writing it in terms of y instead. So how do I solve for x to make it an x equals equation? Square root it. What do we always put in front of a square root? Plus minus square root of y. The nice thing about this problem is they only use the top half, so you only use plus, which is kind of nice. So we really are just going to use positive y. So that means our lower bound is 2, our upper bound is 6. Our function is square root y, and then that's our height, and our width is dy. Good. So you basically write it the same way, you just do everything in terms of y instead of everything in terms of x.
What if you do summation?
We're going to do it. We just haven't done it yet.
Oh, because it's not for the... Okay.
So we're doing definite integral, and then we're going to go ahead and do the limit of sums. Okay. So instead of having delta x, we're going to have delta y this time. So what's your delta y? Yeah, 4 over n, so 6 minus 2 over n, which is 4 over n. And then we're going to have y sub I, since we're plugging in y's this time instead of plugging in x's. So that would be 4 over n I plus 2. Okay. So we're going to say the limit as n goes to infinity of 4 over n is the summation from I equals 1 to n, and then we're going to have the square root of 4 over n I plus 2.
Could you put brackets around that, or is it just not necessary?
It's not necessary because the square root is a grouping symbol already. If you want to put brackets, you are not wrong. The brackets are a grouping symbol as well. Okay. So you guys are going to go ahead and do that. When you get down here, you are not going to be evaluating with the calculator. I'm going to show you guys how to do that later. But I do like the idea of you guys drawing this out, seeing what it is you're actually finding the area of, and I want you to write a limit of sums for each of these.
Along with the integral?
Yep. So the integral's already there for you. So you're basically going to draw a picture of what it represents, and then you're going to write the limit of sums. Okay. Mm-hmm. Okay, and then for the last page, we haven't gotten to this yet, but you are going to go down, and you're just going to put a little x through 28. Don't X it out like terribly completely. We might come back and do that one tomorrow. You have to use a calculator, and we just haven't done that part yet. Okay. Yeah, 28 is the only one you're skipping. Then go ahead and go back to your notes. We're going to do the last little part of our notes, which is properties of integrals. So some of you guys had noticed it already, and you were kind of asking like what happens if the upper bound and the lower bound switch places. So this is the way the integral is supposed to be written, where the upper bound is b and the lower bound is a. It's written in the right order. So if we were were to switch them and say we have A at the top and B at the bottom, so we're doing backwards order, then we just need to put a negative sign in front of this to make it so these two things are equal. So when you switch the upper bound and the lower bound and you have them in the wrong order, it just takes that answer and it makes it negative. So if they gave you something in the wrong order and you want to switch it back to being represented the correct way, then you would just say the negative version of that is the correct way. Okay. Some of you guys figured this one out already. If your upper bound and your lower bound are the same number, then what's your area? 0. If you have an upper bound and a lower bound and your function is a constant function, like it's just a number, that means that your function is like a horizontal line like that. So this is like a y coordinate of c. Then that would say like this is your a coordinate, that's your b. So what you're actually finding is that rectangle right there. So we would say that the area of this rectangle is the base, which would be b minus a, whatever that length is, multiplied by c. And so we would say this is c times b minus a. And that only works if your function is a constant function because you are making a perfect rectangle from the function itself. Yeah.
Is that saying through the C or is that C the?
That c is like in place of f of x. So it's saying that the function, this is c times b minus a. The c that I did right here was labeling my picture.
Okay.
All right, the next one is saying you have a function, the function itself has a coefficient in front of it. What you can do with the property of integrals is you can take that coefficient and pull it out in the front. This property is very common, we'll use that one a lot. The next one says, what if you have a function or two different functions that you're adding together? Really, we're going to think of this as a function that has multiple terms. You have one term plus another term, and that's what makes up your function. If that's the case, you can integrate them separately. So you can find the integral of f of x first, find the integral of g of x, and then just add them together. So we're going to say that this is the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So you could work with them separately and just add your answers together. Sometimes it makes sense to do that, sometimes you won't really care. Okay? I would say that 4 and 5 are the most common properties that we'll work with. Those will be happening all the time. All right, and then number 6 says if you're looking at one function and you find the integral from a to b, and then you find the same function but from b to c, and you're adding those together, that's the same as if you found from a to c all at once. And that's kind of the idea of the very first example we did where we had one shape and we had another shape and then we added them together to get the whole thing. It's the same idea. Okay, so we can actually go back to that practice assignment. We can fill in some of the ones we skipped. And then we'll do some more examples of our notes. So don't put your notes away because we're going to finish those examples. But for number 1 for part E, it said to find, instead of saying from 2 as the lower bound to 4 as the upper bound, it said from 4 as the lower bound to 2 as the upper bound. So that just means it's the negative version of what the answer was. So from 2 to 4, you had an area of 6. So from 4 to 2, you're going to have an area of negative 6. So if the numbers are written from biggest to smallest, they're written in backwards order, then that means it's the opposite sign of what it should have been. Okay? So same thing's going to happen for letter D of question 2. If you're going from 10 to 7 instead of 7 to 10, because you're going backwards. So we have 3 halves plus 3 plus another 3 halves, which makes, that would be 6 again, so in this case it would be negative 6. Now, part A had a coefficient of 2 in the front, so what we can do is we can just pull out that 2 in the front and say that we're looking for double the area from 0 to 1. So the area from 0 to 1 was 1, so if we're looking for double of that, that's 2. So 2 times an area of 1 is an area of 2. Okay. Now we're going to go back to our notes and finish. We have 2 examples left. Okay. So example 5 says to evaluate this function from 0 to 1. So what we're going to do is we're actually going to use 3 different properties at the same time to kind of split this apart and make it pieces that we can work with. So I'm going to say we have from 0 to 1 of 4 dx. And then we're going to do from 0 to 1 of x squared, because that is something we've already worked with. You guys remember the area of a parabola from 0 to 1? It's different when we didn't have Thanksgiving break in between, but this is one we actually found on Tuesday, the notes that you had before Tuesday. It was an area of 1/3. You guys kind of remember that? Yeah. So this x squared has a 3 in the front. So I'm going to pull out that coefficient of 3 in the front and then say the area from 0 to 1 of x squared, making sure I've got the dx on there. So if we use the properties of integrals to solve for this, then for the first one, since that's a constant, we're going to say 4 times upper bound minus lower bound in parentheses. So that's how you evaluate if you have a constant. Plus 3 times whatever result I get for this. And we just knew this is the only, literally the only function we can evaluate right now is from 0 to 1 of a parabola, because that's the only thing that we've looked at so far. So from 0 to 1 of the parabola was of an area of 1/3. That was something that we found before we went on Thanksgiving break. So what would this area be total? Yeah, it'd be 4 plus 1, which is 5. Okay. Right, if we look at the next one is using that last property that you guys could see. So it says that if from 0 to 10 is 17, and from 0 to 8 is 12, then what do you have from 8 to 10? So I'm going to write this out. Some of you guys might have the answer already in your head. Some of you guys might be like, oh, that's way too many letters. So I'm just going to write out the property first. The property says if 0 to 10 is the entire piece of the picture that you're looking at, then if we were to break it up, we could say that if we have from 0 to 8, then all we would have to do to get the rest of the picture is add 8 to 10. So 0 to 8 plus 8 to 10 is actually the entire thing from 0 to 10. So 0 to 8 plus 8 to 10 would give us the whole thing from 0 to 10. That's what the last property says. So if we know that 0 to 10 is 17 and 0 to 10 is 12, then 8 to 10 must have been 5. Yeah. Okay. So again, if we were to, we can like draw a picture of that. So we'll say right here, this area right here is 12. and the area of the whole thing is 17. And so they're saying if this whole area is 17 and that area is 12, then what's this area right here? And it's 5. It would have to be 5.
So, because the
Integral from 0 to
So they're saying the whole thing is 17,
Yes, and then
and this part is 12.
some 12 plus something.
So what should that one be?
36.